All right, shall we begin? Hi, everyone. Thank you so much for joining us today. My name is Joe, and I'm here as part of the Open TMP community. We are an open source community focused on threshold multi-party protocols. What we're building together is a foundation that makes multi-party computation more accessible, secure, and practical for developers and enterprises. In simple terms, our mission is to provide a trust and privacy layer that enables collaborative AI and secure data cooperation. We're really excited to share ideas and foster discussion with all of you. To take us deeper into the topic, I'd like to introduce our researcher, Haoyang. He'll walk us through the fundamentals of secure multi-computation, what it is, why it matters, and how it's being applied in practice.
Hello, will everyone say it?
可以听到。顺便
OK，
提醒一下大家，就是分享者虽然是英文分享，但最后大家也可以拿中文来讨论啊、提问这个。OK，
OK，
行，那您开始就好了。
shall begin. So, good night, everyone. Welcome to our seminar. My name is Liu Haoyang, the research engineer at Space Labs. Today, I want to share something interesting with you: secure multi-party communication, or MPC. Okay. First, let me ask you a question to think about. It's called the millionaires meet and want to know who's richer, but they don't want to reveal their exact net worth to each other. This sounds strange, right? How can we compare two numbers without knowing their values? MPC provides a solution. We can actually solve this problem using a specific MPC protocol called Gablot circuits, and I will explain it in more detail later. Although we don't know the specifics of how Gablot circuits works, we can specifically on the general process. First, the two individuals must input their data into a system, and here we could call it a black box. However, they do not retrieve any other information from this black box, except for the final comparison result. In fact, this can also be seen as a general process of many MPC protocols. And the stable difference between different protocols are simply the difference in the composition of this black box. Okay. From this minimalist problem, we could know the core concepts of MPC. The first is privacy. We must ensure that the input data from all parties involved in the communication is secure, prudent, and want to be exposed to others. Second is correctness. We must guarantee that the computation result is accurate. Finally, is robustness. Even if one or more participants transmit incorrect data, we should try our best to ensure the accuracy of the final result. MPC has many components, but there have three main algorithms are widely used and well known. And when later we talk about the protocols later, we will find that those algorithms are the basis of another mainstream advanced protocols. The first is Gablot circuits. It was proposed by Professor Andrew Liu to solve that minimalist problem. The core idea is to convert a logical comparison of two numbers into a Boolean circuit. By incorporating and gathering this Boolean circuit, we can achieve prevent preserving communication. The second is secret sharing. The core idea here is to split a secret, and here we could just simply understand it as a number into multiple parts using some method. For example, as shown in this diagram, there are 5 shares, and you need to have a certain number of them, like 3 shares, to reconstruct the original number. It may be sound mysterious, but the implication is quite simple. The simplest form is called additive secret sharing. For instance, I have the number 8, and I split it into 2 and 6, and give them to Alice and Bob respectively. And we know that 2 plus 6 is 8, right? However, from Alice's perspective, she only knows the number 2. Without knowing the number in Bob's formation, she can't guess my original number. Maybe 3, maybe 4, or 100, or 10,000. Yes, so this simple method allows us to achieve data privacy and transmission. However, we should note that adaptive secret sharing requires that every secret shared must be preserved. Otherwise, the resulting number will be incorrect. To ensure the accuracy of the final recovery number, even when the data loss or incorrect, a method called Shamir secret sharing is advised, and now it's commonly used in industry production. Okay. The last one is homomorphic encryptation. Homomorphic is a concept from our abstract algebra in mathematics. And as the name suggests, it's not very easy to understand. However, I can give you a small example to illustrate its properties. Let's say I have number 5 and 3, and Alice has a calculator. I want Alice to help me compute 5 plus 3. The direct way for me is just to tell Alice 5 and 3. But in many situations, I don't want Alice to know my original inputs. So I could use homomorphic encryptation. I could use homomorphic encryptation to turn 5 into another number, E5, and 3 into another number, E3. And send those 2 incorporated numbers to Alice. After Alice performs the calculation, she gets another number. Let's call it E8. The medical thing is that when we calculate E8, the result is 8, and we all know 5 plus 3 is 8. Yeah, this is the amazing property of homomorphic encryptation. The result of calculation on the plain text is related to the result of the calculation on the ciphertext. In a way, operations on the ciphertext represent operations on the plain text. To summarize, secret sharing is the simplest, and I believe you can feel that. It's mainly used for automatic computations like addition and multiplication. Gablet circuits are of medium difficulty and are primarily used for logical computations. And the homomorphic encryptation is the most complex and challenging. It's not yet been widely adapted for large-scale industrial applications, and many of its advanced algorithms are still in the theoretical or experimental stages. Okay, now I will introduce a few classical MPC protocols. The first one is still the gablet circuits because it's the fundamental protocol of the field of MPC. Is the first protocol. Professor Andrew Liu is regarded as the founding father of MPC for proposing this algorithm. So it's very important. It can be divided into a few steps. First, we can always convert a logical comparison of 2 numbers into a Boolean circuit. Let's consider a scenario where Alice and Bob each have a number 1 or 0, and they want to compare them. Let's assume Alice converts this logical comparison into a Boolean circuit. This circuit has several inputs, outputs, and wires. Alice first encrypts the wires and then encrypts and shuffles the truth table. Then Alice sends this result of Bob. Bob uses a method called oblivious transfer to get the encrypted key for his input from Alice. Oblivious transfer ensures that while Alice has 2 keys, Bob can only obtain one he needs, and Alice don't know which key he chooses. Then Bob uses the key to decree and restore the truth table, and finally he could get the comparison result. Okay. And the second one is BGW. This protocol is named after its 3 inventors. It uses secret sharing to perform automatic computations. Let's assume a scenario where n people want to compute a function together. So if people can split their previous data into a number of shares and send them to others. Okay. This way, when computing addition, the final sum could change, but each person's previous data is preserved. You could think about the addictive secret sharing. The final sum is never changed. But computing multiplication is a bit more complex, and it requires each person to perform additional communication, but it still be done at a little complex, yes. And the third protocol is SPDZ. This is another protocol related to secret sharing. The specific idea is that when we compute multiplication, we could introduce an area called bill triplets to reduce the communication between different parties. SPDZ is divided into 2 phases, an offline phase and an online phase. In the offline phase, we can use certain methods to compute the bill triplets and store them. Okay. And in the online phase, we can call upon the bill triplets to perform multiplications on the sequence. And here you can see how MPC uses bill triplets for inter-shared multiplication. Bill triplets are secret sharing of 3 numbers, A, B, and A times B, C. For any participants given 2 shares, X and Y, using bill triplet, we can calculate the share of X times Y. And using this formula, you could see it here. And this allows inter-shared multiplication. So because of the offline phase and online phase, SPDZ now is a very computationally efficiency and currently a mainstream MPC protocol. Okay, next I will introduce some industrial applications of MPC. First, there are threshold signature schemes, TSS. This means that simple people each hold a partial key, and a digital signature is only guaranteed when a certain number of participants cooperate. And as you can see the image on the right, the key is shared, but the digital signatures can only be performed with at least 2 people. According to this diagram, we know TSS is actually a protocol related to secret sharing. So secret sharing is widely used, and many advanced protocols are based on it. And this diagram is very similar to the diagram of secret sharing. The only difference is the final result. Here is a signature generation. So what is the digital signature? It's very hard to tell its principles, but digital signatures are very similar to real-world signatures. they confirm to others that the data is yours and has not been altered since you signed it. Due to this characteristic, TSS is widely used in cryptocurrency and blockchain to enhance security and reliability. Okay. And that is prevent that intersection, or PSI. You can see the diagram on the right. A has a blue ball, a green square, and a yellow triangle. B has a green square, a yellow star, and a red diamond. 0 PSI. A and B can find that part of their data that are similar or individual. However, A will not know B remaining data. It means that A will never know that B has a star and a diamond. Due to this property, PSI has very wide applications. Besides the financial sector, it's also used in advising, healthcare, and another fields. And we know that the data held by individuals or institutions is not very comprehensive, and the data volume is not very large. But through prevent that intersection, different institutions can collaborate to create a shared database of similar features. Okay. And finally, there is the MPC application in the field of artificial intelligence. We know that AI training is inseparable from the quality of data set. However, in many cases, institutions with good high-quality data set don't have the capability to train an AI model on their own, while institutions that can train AI models are very rich for high-quality data sets. However, it's impossible to provide high-quality data sets directly to AI model owners. Currently, the most mainstream approach is feed learning proposed by Google. The general idea behind the feed learning is that to separate a protein of the model to be trained and distribute to the owners of high-quality data sets. Those institutions can then perform training at a minimal cost, and the training results are then transmitted back to the model owners. However, it's important to note that even with only the training result, it's still possible to infer some characteristics of the original data set. So in a sense, feed learning is not completely proven to protect. So therefore, many people are currently experimenting with the combined MPC and the feed learning to make the learning process more prudent and secure. Of course, we could also imagine another scenario, like using MPC in AI applications. When using a large model, we can incorporate our questions so that the large model's owner doesn't know them. Today, AI is rapidly developing, and it's very easy for everyone to use various AI models. Like in China, you could use Doubao or Yuanbao or DeepSeek. However, this naturally creates a problem. Every sentence and the message we enter in the chat box must first to be transmitted to the cloud-based model, and then the response is transmitted to us. This effectively allows us input to be accessed by the owners of those AI models. Given public privacy concerns, I believe privacy protection for cloud-based model applications will become a new development privilege. However, there is currently no efficient solution for this requirement so far. So for now, we have to reduce that our API calls or website usage of ChatGPT or Gemini or other AI models unknown to the model manufacturers. Okay. The field of MPC itself also has room for development. For example, can we better integrate homomorphic encryption into another MPC component? Can we use zero-knowledge platforms to make MPC protocols more secure? Can we design a dedicated computing CPU for MPC? And most importantly, we know that quantum computing is very powerful and can quickly solve the problem of large number factorization. However, many MPC protocols are based on large number factorization. So when quantum computing becomes widely available, can we design efficiency and powerful MPC algorithms to resist attacks from quantum computers? I'm personally very excited about this. Okay. Finally, with the increasing emphasis on the privacy and security from governments, private institutions, and the general public, as well as the arrival of distributed worlds like blockchain and Web3, and the rapid development of AI, secure multi-party communication is becoming more important in more and more fields. And our company's goal is to combine theoretical research with industrial applications to gradually drive the development of MPC. And that's the end of my presentation. Thank you.
All right, perfect. Thank you, Haoyang, for that clear and insightful presentation. And thank you all for being with us today. What we've seen is how secure multi-party computation works, from its fundamental concepts to the classic protocols, and to how it's being applied in areas like digital signature, private data queries, and even AI training and inference. At OpenTMP, this is exactly what we are working on, turning advanced cryptographic research into real-world infrastructure that makes AI and data collaboration more secure, private, and trustworthy, so that in the long run, we can truly make collaborative AI possible. We'll continue pushing forward in this space, and we're always eager to connect with people and communities who share the same vision. Please follow us on Twitter, OpenTMP. I've shared the link in the Zoom chat. And thanks again for joining us. And a big thank you as well to Cosette for co-hosting this event. We look forward to many more conversation and collaboration to come.